Now we move to the tensor product, and the tensor product is very helpful when we are dealing with multi-qubits and the multi-qubit gates. Let's have a look on the following example. If you have a single qubit, the quantum state is expressed as alpha 0 plus beta 1. Then our computational space is two-dimensional. We have here 0 and we have here 1. So this is our state Q. What if we have a quantum computer of 2 qubits? Then the computational space, or the space of which we can use to compute or express a 2-qubit state or any qubit state, is actually 2 to power n. So this is the size of the Hilbert space. And hence, if we have 2 qubits, we call them Q0 and the Q1, then we will have 2 to power n. And 2 to power n, if n equal 2, then we have 2 to power 2, we'll have 4 states or dimensions. Then we are going to have a table. This Q0, Q1 could be 0, 0, they could be 1, 0, they could be 0 and 1, and they could be 1, 1. So we have 4 combinations or 4 situations, 4 probable situations which can exist. We can have kit 0, 0, kit 1, 0, kit 0, 1, and kit 1, 1. Similarly, if we have 3-qubit quantum computer, we are going to have 2 to power n, then we have about 8 states, and this will be kit 0, 0, 0, kit 1, 0, 0, kit 0, 1, 0, kit 0, 0, 1, then kit 1, 1, 0, kit 0, 1, 1, and kit 1, 0, 1, and the kit 1, 1, 1. Okay, so hopefully they are correct. So we have 8 possible and probable states coming out of 3 qubits. So how we can do the quantum state representation of multi-qubit mathematically? We use a tensor product for that. If we have 2 quantum states, psi and phi, then the tensor product would mean that we make an expression where we involve the state of the first qubit and the state of the second qubit, and then we end up having the state representation in 4 dimensions, which spans, or in the space which spans the dimension of the first qubit and the dimensions of the second qubit. Let's see how. So we can have a state Q0 in the ground state, so equal to kit 0, and then we can have kit 1, this is also in state 0. Then to express the combined state of both qubits, Q0 and Q1, we use the tensor product, so we multiply them tensorically, and we make sort of distribution. So this is a column vector representation of the first qubit. We have 1, 0, then tensor times 1, 0, then we're going to have 0 times 1, 0. This is a column vector still, but now it is 4 by 1 column vector. So it has 4 rows and 1 column. This will give me 1, 0, 0, 0. In this new space, I know that if I have 2 qubits quantum computer of n equal 2, if 2 to power 2, then I have 4 states, and those 4 states are all permutations or the possible combinations of the zeros and ones of each qubit. So we are going to have kit 0, 0, kit 0, 1, kit 1, 0, and the kit 1, 1. Then I can use this to label my bases. So I can say, okay, this number is corresponding to the kit 0, 0. This number is corresponding to the kit 1, 0. This number is corresponding to the kit 0, 1. And this number is corresponding to 1, 1. So this is the coefficient times this one. So if I have 2 qubits and each qubit is initialized to the ground state, this basically means that the combined state is just kit 0, 0. This is a combined state. So the tensor product is helpful in this. And as we are going to see shortly, it's also helpful to understand the gates. Similarly, I can have 2 qubits where Q0 is initialized in the ground state, and I can have Q1 initialized in the excited state, or kit 1, and I wanted to express using the tensor product the combined state. So I have kit 0, kit 1, so it means that I multiply tensoric or all times Q0 times Q1, and that would mean that I have 0, 1. Then if I do that, of course, I can do it symbolically, so that will give immediately to me 0, 1, and I can do it numerically because I'm allowed to do this by the tensor properties. You can also check this with a linear algebra course. We have multiple linear algebra courses on the channel. If I do that, then I end up having I multiply tensorically two vectors, and then following the same rule, then the number 1 will be distributed. So we're gonna have 1 times the column vector of 0, 1. I'm gonna have 0 times the column vector 0, 1. This will give me 0, 1, 0, 0. And if I look at this vector, I'm gonna find that, okay, the first number is actually kit 0, 0. The second one, the number is kit 0, 1. And then the third one is kit 1, 0. And the fourth one is kit 1, 1. So indeed, I landed here. The coefficient is 1. So I have like sort of 1 times this one, and the rest are zeros. So we see the advantage of this. To summarize, I have here some coefficients, alpha, beta, gamma, and eta. And each number of those represents a coefficient to a particular quantum state or eigenstate of the space. So I have here kit 0, 0. Here this is corresponding to kit 0, 1. This number corresponds to kit 1, 0. And this number corresponds to kit 1, 1. So the total state generally is expressed as Q0, Q1 equal alpha kit 0, 0 plus beta kit 0, 1 plus gamma kit 1, 0 plus eta kit 1, 1. So this is for 2-qubit quantum computer. So we see we have expressed now the computational space or the Hilbert space of 2 qubits using the tensor product. The tensor product is very helpful to express and span the space of multi-qubits. We have seen the example of 2 qubits. This also could be extended using the same methodology. Then you are going to apply more and more tensor products for the first qubit, tensor product with the second qubit, tensor product with the third qubits, and so on to get the combined state. Further, you can use the same to form the quantum gate of multi-qubits. So the gate can act on a specific qubit and leave the rest untouched, and so on. So you can also do example 3 and example 4 on your own, and then you can have fun with them. Now we move to the multi-qubits and the multi-qubit gates. So the gates like the X and the H are single qubit gates that act on a single qubit. So this is why it's called single qubit, because its action is only involving a single qubit at a time. So typically the quantum computers, they have multiple qubits, hundreds, and presumably in the near future that will be thousands and thousands of qubits. And then you need a gate that act on a single qubits, but also you need gates that can act on multi-qubits, like the CNOT gates, which those gates are very important for the creation of the entanglement, for example. Then the CNOT gate is an obvious example of a 2-qubit gate, and this one can flip the second qubit if the first qubit in state 1. So it's a conditional gate. If the first qubit, or we call it the control qubit, is in a particular state 1, then it will act on the target qubit. If not, it will leave it untouched. So if we have a 2 quantum computer here, we have Q0, then we have Q1, then this is how we represent CNOT gate. This one, we call it the control node, and this one is called the control qubit. This one is my target qubit. And this gate is conditional. So based on the result and the sampling that you do here, this gate will decide to apply this action or not. So we have the following truth table. If Q0 is in 0, the result will be do nothing to Q1. If Q0 is 1, then apply X gate to Q1. So it's a conditional gate, which based on this property, either it will take this action or not. What we see here is the action represented mathematically. So the action of the CNOT gate denoted as Cx on 2 qubits can be represented as Q0, Q1. So the Cx acts on Q0 and the Q1. There is also the subscripts need to be adapted here to 0 and 1. Okay, so we have the CNOT gate is represented by this matrix. This is the matrix representation, and we have to bear in mind that this is a matrix representation in big Indian representation, because in Qiskit, they use little Indian. So in big Indian, you number the qubits from left to right, but in little Indian, you number them from right to left. Okay, so now this is the action of the CNOT gate. So once you have the matrix representation, if you look at it, you have sort of the identity here, and then you have the X gate here. So the identity is actually acting on the first qubit, because literally it doesn't do anything to the first qubit. And then the second block of the matrix is the X gate. Then together, if you act on 2 qubits initialized in the ground state, you are not gonna get anything because the two qubits are in zero, so the control qubit is in zero state. Then the CNOT gate won't do any action or want to do anything. So if we have acting on kit 0, 0, then it means that we have the following matrix acting with us. We have 1, 0, 0, 0, 0, 1, 0, 0, and then we have 0, 0, 0, 1, then 0, 0, 1, 0. This is will act on 0, 0, and as we have seen, that's a column vector starts with 1 and the rest are zeros. And here we see the representation of the X gate, and here we see the representation of the identity in this 4x4 matrix because it's a two-qubit state. So now the result of this will give me 0, 0, or the same column vector, which will be kit 0, 0. It means that for my control qubit and the target qubit, this one is a control, this one is a target qubit. So since this is 0, the CNOT gate won't do anything. And if this is 1, then the CNOT gate will actually take an action. So let's get to this state. CX acts on 1, 0, which means that we can have identity block acting on this 0, 0, 1, 0, because as we have seen, this will respond to kit 0, 0, this kit 0, 1, this kit 1, 0, and this is kit 1, 1. If we do that, we get a resulting column vector which has 3 zeros and 1. And here is the thing, why this has happened, because if you look here, we have the Q0 and the Q1. Here, Q0 is actually 1 and the Q1 is actually 0. So since it is initialized with 1, then the CNOT gate, when it's applying, will have a look and the peak at Q0. If Q0 is 1, then it will apply the X gate on Q1. So the X gate here will be applied, and this the result will be that the 0 of Q1 will turn out to be 1. Then this is why you get this result. You get kit 1, 1, because the Q1 has been flipped from 0 to 1, and the rest are zeros. And similarly, you can do the same with kit 1, 1. So both qubits are initialized into kits of 1s. And then you can see that you can flip the second. Instead of being in 1, it will turn out to be in 0. Here we see the circuit representation of the CNOT gate. Of course, I have drawn it now. So this is circuit representation. And this is a little of truth table of the CNOT gate. If you start with an input 0, 0, the CNOT gate won't do anything and it will get the same. If you start with 0, 1, you will get the same because the first qubit, which is the control qubit, is 0. So the activation will happen only when it turns out to be 1, like here. So if the first qubit is 1, the second is 0, then please flip the second, then you get 1, 1. If the first is 1, the second is 1, please flip the second, and then we'll get 1, 0.